The object-oriented paradigm can be quite neatly summed up as simply privileging data over action. That is, in contrast to procedural programming, where we approach our problem by decomposing it into a series of actions, aka functions. In object-oriented programming, we approach our problem by trying first to decompose it into a bunch of data types. Now, of course, in either paradigm, you end up defining in your code both actions and data types. So the difference really hinges upon what do we think about first. In procedural programming, we think in terms of functions, and then as a secondary matter we consider the actual data which those functions act upon. In object-oriented programming, we simply reverse that. We come up with our data types first, and then we have to decide what operations we need associated with those data types. This inversion in our approach is really just by itself quite subtle, but in practice there's a bit more to object-oriented programming. There are a few principles which we'll discuss. The interesting question then is, what is the point? Does object-oriented programming really have virtues that procedural programming does not? So that's something we'll discuss along the way as well. Many popular programming languages today are considered object-oriented languages because they include features which assist or even encourage the programmer to program in an object-oriented style. So, for example, here are 6 popular current languages, 3 of which are static and considered object-oriented languages, Java, C#, and C++, and 3 other dynamic languages with object-oriented features, JavaScript, Python, and Ruby. Now, we've already covered JavaScript, and you may be wondering what were the object-oriented features. Well, JavaScript is actually kind of an oddball. JavaScript's approach to object-oriented programming is actually very unusual. It uses a mechanism called prototypical inheritance, which is what we saw in the language when objects got linked together by use of the new operator. We covered how that feature works and what exactly it does, but we didn't really discuss why it exists in the language. What's the point? That's something you should have a notion of by the time we finish this unit. Again, though, understand that JavaScript is really kind of an oddball. Where JavaScript uses what's called prototypical inheritance, most other object-oriented languages use a feature called classes and class-based inheritance. So, what is a class? Well, a class is simply a data type definition. A class is synonymous with a data type. And each class, each data type, is defined by its members. And members come in 2 basic kinds. First, fields are the data members. They are the data which actually makes up this data type. So, for example, if I'm creating a class cat to represent a cat, well then a cat is made up of a bunch of different pieces of data, like say a string for its name or a number for its number of remaining lives, and perhaps other fields to represent things like say its age and what color it is and so forth. So when we say we're defining a data type, we're defining a compound data type, a data type that's composed of a bunch of other pieces of data. And those pieces of data, those fields, they can be any kind of data that exists in your language, so they can be the built-in things like strings and numbers, but their data type might be some other class. So, for example, if I create a class to represent a car, well, a car has a bunch of pieces, one of which is a steering wheel, so I might have in my car class a field which is an instance of the steering wheel class. And note that term instance. When we create a class, that class is like a blueprint for actual pieces of data. Each actual example of that type we create is called an instance, or more generically and more confusingly often called an object. So that's the point of a class. It's a blueprint from which we produce actual pieces of data, called instances or sometimes objects. The other kind of member of a class is called a method. A method basically is a function associated with that class. The idea is that these methods are the operations for acting upon that type of data. Now, one important thing to understand is that when we instantiate a class, that is, we produce an instance from a class, that instance, that object, in memory must consist of all of the fields defined in the class. So say if a class representing a cat has a field representing its number of lives, well then each cat instance we produce has its own number of lives field, because every cat has its own number of lives. My cat has 7 lives left, yours has 5. With methods, however, it's a different story. Both of our cats meow, because that's just a thing that cats do, so the class cat has a meow method. However, this doesn't mean that the instances produced from that class, the cat instances, need their own meow method. There's just one piece of code associated with both of those objects. Each object doesn't have to have its own copy of the method. There's just one copy of the method in memory. When we invoke this method, which cat instance does the meowing gets determined by which cat instance is passed to the method. So again, keep in mind, when we instantiate a class, that instance object has its own copy of the fields, but not its own copy of the methods. The first principle of object-oriented programming we'll discuss is called encapsulation. The idea of encapsulation is simply that the fields of an object, an instance, should only be read or written by methods of that instance's class. So say the number of lives field of the cat class, the principle of encapsulation says that that field should only be read or written by methods of the cat class, not by methods of any other class or by any other code. So when we're writing code outside of the cat class, that is not inside the methods of the cat class, the only way we're supposed to be interacting with the fields of any cat object is by invoking methods of the cat class. If this here represents some instance of a class with 3 fields and 4 methods, remember I did say that each instance doesn't actually have its own copy of the methods, so these methods aren't really here in this particular instance, they're in the class itself. But that aside, if we want to read or write one of these fields, we should not do so directly from outside the object. Only the methods of the class should be directly reading and writing these fields. From outside the class, we only interact with the fields indirectly by invoking the methods. The thinking here is that when you create a class, the methods you give that class encapsulate, they encompass all of the knowledge of what is meant to be done with the data that makes up that data type. The hope is that if we strictly follow this principle, our code will end up very neatly and cleanly modularized, thus allowing us to easily make changes, to add features, and to fix bugs. When you ignore this principle, data in your code ends up getting read and written from all different places in code. You very easily end up with what's called spaghetti code, which is extremely difficult to understand and therefore very difficult to fix and modify. Now, as we'll see when we get into actual object-oriented languages, some of them are more strict about enforcing this principle of encapsulation than others. Generally, the static languages are more rigid, whereas the dynamic languages are totally loosey-goosey and allow you to do anything you want. So say, if you do object-oriented programming in JavaScript or Python, there's no mechanism in the language that really prevents you from mucking with any field of any object anywhere in code, basically. Lastly, when talking about encapsulation, we use these 2 terms, public and private. The public members of a class we say are visible anywhere, meaning it's okay to access them from outside their own class. The private members, in contrast, are the ones which are only meant to be accessed by methods of their own class. So when you follow the principle of encapsulation strictly, all fields should be kept private. Methods, on the other hand, may either be private or public. Generally, you would make them public by default, but there might be some methods which you don't want to have invoked outside of the class, so you would keep them private. Again, some languages actually have mechanisms to enforce these access levels, public and private, others do not. The second important principle of object-oriented programming is called inheritance. The idea of inheritance is simply that some data types, some classes, may overlap such that in fact one data type has all of the same stuff found in another. When one data type has all the same stuff as another, it just has more stuff, then in that one case we say that the one data type is a subtype of the other. When our programming language has a mechanism for inheritance, it allows us to formalize these relationships. So, for example, say we have 3 classes, one called animal with the members A, B, and C, one called mammal with the members D and E, and another cat with the members F and G. For our purposes here, it doesn't matter which of these members of the classes are fields and which are methods. In any case, if we relate together these classes by inheritance, such that, say, cat inherits from mammal and mammal inherits from animal, well, what that will mean is that the mammal class will automatically inherit all of the members of the animal class, and in turn the cat class will inherit all of the members of the mammal class, including the things which mammal itself inherited from animal. So here you can see that the cat class has the member E as defined in mammal, and also has, say, the member B as defined in animal. So even though when we wrote the cat class we only specified it has members F and G, because we specified that cat inherits from mammal and mammal inherits from animal, then cat has the members A, B, C, D, and E. This is automatic inheritance. If our language didn't have any kind of inheritance mechanism, then when we had two related classes, such that one is a subtype of the other, as say cat here is a subtype of mammal and mammal is a subtype of animal, then when we define these subtypes, we would end up manually including all of these members. So in the mammal class, say, we would actually have to give the mammal class explicitly members A, B, and C. With inheritance, it's simply done automatically. So we don't have to make sure, say, that A defined in mammal is actually the same as defined in animal, because with inheritance, it's automatically going to be the same. Now, one important thing to get straight here is the terminology we use when talking about classes related by inheritance. Here in this example, we would say that mammal and cat are subtypes of animal, and cat is a subtype of mammal. And conversely, we could say that animal is a supertype of mammal and cat, and mammal is a supertype of cat. Alternatively, instead of saying subtype, we could say descendant, and instead of saying supertype, we can say ancestor. So for example, animal here is an ancestor of cat, and cat is a descendant of animal. And then confusingly, on top of this, we often use the terms parent and child, but these terms are only used to refer to the direct ancestor and the direct descendant. So here, for example, animal is the parent of mammal, and mammal is a child of animal. Now, I'm sure you're also puzzled here by what's the significance, what's so great about inheritance, why have some classes be subtypes of others? Well, it simply turns out that in some circumstances, the ability to create subtypes is just quite useful. The most obvious use for inheritance is when we're modeling real-world objects, as we presumably are doing here with these classes animal, mammal, and cat. Because in the real world you do have things which effectively form this kind of hierarchy, where a cat is a kind of mammal and a mammal is a kind of animal. So when we create classes to represent those three things, it makes sense that we put them in a hierarchy of inheritance. If a cat truly is a type of mammal, just a more specific kind of mammal, then it's going to need all of the same things that the mammal class has, just it's going to have more stuff. Like, for example, all mammals eat and sleep, so it makes sense that the mammal class might have methods called eat and sleep for eating and sleeping, but cats do some things which only cats do, not all mammals, like, say, meow and purr. So if you had a meow method, you would put that in the cat class, not the mammal class. Now, in practice, with the vast majority of object-oriented code, the classes we define don't really model real-world objects. They tend to be much more abstract sorts of things. When dealing with abstract entities, it's often not so obvious when one type is truly a subtype of another or not. However, when you do successfully identify such relationships and so create a proper inheritance relationship in your code, this may end up saving you quite a bit of work by sparing you from having to duplicate a lot of functionality in one class that already exists in another. In fact, it's fairly common when working with an existing program that any new feature you might add can be successfully implemented by simply taking an existing class in your code and extending it, that is, producing a subtype of that class. When this works well, it allows you to focus on just writing the code for the new functionality, not having to duplicate already existing stuff. Now, on the other hand, it's actually really easy for learners to get the misimpression that they should be using inheritance all over the place. This is not the case. You need to think before you use inheritance. The simple rule you should keep in mind when thinking about using inheritance is ask yourself, is the relationship between these two classes really a is-a relationship or a has-a relationship? In a proper inheritance relationship, instances of the child class can be considered more specific versions of the parent class. So, for example, a cat is a kind of mammal. That's an is-a relationship, so it's a proper example of inheritance. In other cases where you might be tempted to use inheritance, the true relationship is not an inheritance relationship, but a composition relationship. For example, a car is composed of many parts, including a steering wheel. So if we have a car class and a steering wheel, then it makes sense that the car class has a steering wheel field. That's a has-a relationship. It's composition, not inheritance. It would not make sense to have the steering wheel class inherit from the car class because a steering wheel is not a kind of car, and it wouldn't work the other way either. A car is not a kind of steering wheel. If we were going to extend the car class, we would do so with something like Toyota, or DeLorean, or sedan. Something which is a car, just a more specific kind of car. So, when thinking about using inheritance, just be sure to ask yourself, is this a is-a relationship or a has-a relationship? In some languages with inheritance, a single class may inherit from more than one class, such that here, say, Kate would grab all the members of both the Ted class and the Milton class. Many other languages, though, say like Java and C#, don't allow this. They only allow single inheritance, such that each class can only inherit from one other. This choice between allowing multiple inheritance or not is mainly a trade-off between simplicity and flexibility. Single inheritance is generally much less confusing, and it means that the language doesn't have to have any sorts of rules to deal with situations like, say, imagine Ted and Milton both have a member named X. Well, then the question is, what happens in Kate? Which X does it inherit? Does it inherit the X from Ted, or does it inherit from Milton? If we have multiple inheritance, our language has to have rules for covering those complex corner cases. In single inheritance languages, we just don't have to think about such cases. On the other hand, multiple inheritance may sometimes come unuseful, as it allows us to take two existing classes and sort of mix them together. What's definitely not allowed in any language, though, is circular inheritance, wherein a class ends up indirectly inheriting from itself, like say here Kate inherits from Ted, but Ted inherits from Jack and Jack from Milton, and then Milton inherits back from Kate. No languages allow this because it simply doesn't make any sense. It's not even clear what it would mean, really. In some object-oriented languages, every class is required to inherit from at least one other class, and by default that class is a special class called the object class, which is built into the language, and exists in effect at the top of the hierarchy. So as we see in our diagram here, every class except object itself is inheriting from some other class. So the object class effectively sits at the top of the hierarchy, such that any class you create is going to be an ancestor of object. The point of this is that the built-in object class is meant to represent just a generic object of any kind, and so it makes sense that any classes you create should be subtypes thereof, because anything you create is going to be an object. We'll see this kind of inheritance tree first in Python and then later in Java. To override in object-oriented programming means to redefine an inherited method. So here, for example, if we have this chain of inheritance from object to Jack to Ted, Lisa, Kate, and then down to Mike, well, if the Jack class is defined to have a method named foo, then all of its descendants will have that method as well. However, if in the Lisa class we define a method also named foo, then Lisa will have that foo instead of the one inherited from Jack, and in fact Kate and Mike will inherit the foo of Lisa, not the foo of Jack. The utility of this is that, yes, a subtype does all of the same things as its ancestors. However, a subtype may need to do that thing in its own specific way. So, like say in the real-world situation where a cat is a kind of mammal and all mammals eat, well, we might choose to override that method eat in the cat class because our cat eats in its own particular way specific to cats. The purpose of overriding is probably a bit clearer if we look at how methods get invoked. In most object-oriented languages, we invoke methods with this syntax of first an expression that returns an object, then a dot, and then the name of the method, followed by, in parentheses, a list of arguments, separated by commas, just like a regular function call. The reason for this syntax is twofold. First, methods generally live in the namespace of their class, so we can't just refer to them directly by name. We need to look for that name in a particular class. So what typically happens in this syntax is that the type of the object tells the language which class to look for that method in. The other reason for this syntax is that when we invoke a method, we somehow need to specify the instance of the class upon which we are invoking that method. In effect, the instance, the object here, gets passed in somehow as an argument to the method. You may recall in JavaScript, there's this special trickery whereby it gets passed to this special word, this. In other languages, there's a different mechanism, but it's the same idea. The object, the instance, somehow has to get passed into the method, while also serving the role of identifying the type, the class, in which we look for the method. Note that method calls, then, are naturally polymorphic. Here, for example, when we call x.foo, which method foo we're calling, which operation, depends upon the type of x. Like, say, looking at the inheritance tree from our overriding example, here if the X expression is a Lisa object or a Kate object or a Mike object, this will define the foo method defined in the Lisa class. If, however, the X expression returns an object of type Ted or Jack, then this will invoke the foo method defined in the Jack class. In most object-oriented languages with classes, you're allowed to give your classes members which are class members rather than instance members. These are members which are members of the class itself, not members of any instances you create. So, say if you give the Jack class an instance field named X, then any Jack instances you create will each have their own copy of that field, X. However, if you define the X field as a class member rather than an instance member, then only the Jack class itself has a copy of the field. Any instances you create do not have their own X field. Now, it's also possible to define class methods rather than instance methods. A class method is a method which you invoke by specifying the class, and no instance gets passed into the method. In truth, class fields and class methods are really not proper object-oriented fields and methods. A class field, in effect, is really just a global variable that happens to live inside some class, and a class method is really just a plain old procedural function that happens to live in some class. I would even go so far as to say that if you use a lot of class fields and class methods in your code really isn't object-oriented at all. It's just procedural programming in disguise. So why are these things allowed at all? Well, in some languages, such as Java, your code is meant to consist entirely of just classes. So if they didn't allow class fields and class methods, or as they call them in Java, static fields and static methods, then you would have no way of writing just a plain old function in Java, or just having a plain old global variable. So in a way, class fields and class methods are just compensation for an odd design decision of not allowing anything other than classes in your code. On the other hand, you do have languages like, say, Python, where you can have just plain functions and plain global variables, but they also have class fields and class methods. So the choice there of whether to make something, say, a regular function or a class method, that's really just a matter of style. Sometimes it just for organizational purposes makes sense to group things into classes, even if they're not really instance fields or instance methods. But be very clear, class fields and class methods, aka static fields and static methods, they are not true members of the class in a proper object-oriented sense. When we create the instances of a class, very commonly we want to do some kind of setup work, and for this purpose we have constructors. A constructor is simply a method which is run when we instantiate a class. So for example, given a cat class, when we instantiate cat, that is, we create a cat object, that new cat object is automatically passed as the instance to the cat's constructor method, and then that cat constructor does presumably whatever setup work is appropriate for a cat object. Now, in many cases, the constructor does nothing more significant than just giving the field's initial default values. In other cases, though, you might need constructors that do much more complex things, like actually run some real code. What's appropriate is really entirely context dependent on what exactly your class does. Another important term in object-oriented programming is interface. The notion of an interface is that you may have two different types, two different classes, which, though perhaps unrelated, share a set of methods in common, and we call that set an interface, because given any object of a class which shares that interface, we can interact with those objects in the same way with this set of methods. Like, say we had three classes, a cat class, a robot class, and a fighter jet class. Well, all three of those kinds of things are things which both move and stop, so they might all have a move method and a stop method, and that would be an interface which they share. So given any object of those three types, we can invoke either of those two methods, those methods of that interface. As we'll see, what happens in dynamic object-oriented languages is the concept of interface is generally not formalized. There's no explicit recognition of interfaces in the language, but then in static languages like Java and C#, there's a mechanism in the language to denote common interfaces between classes. Another term to understand is abstract class. An abstract class is a class which is not meant to be instantiated. Instead, an abstract class is just meant to serve as the parent for other classes. So for example, in your code you may have no need for any, say, mammal objects, but you do have dog and cat objects, so it makes sense to create an abstract class mammal from which you extend the dog and cat classes. In some languages, like Python, there's no formal mechanism for creating abstract classes. You just create a regular class and just never instantiate it. But in static languages like Java, there's usually an explicit mechanism for abstract classes, whereby when you create a class and explicitly declare that it is abstract, the language does not let you instantiate that class. So it's a mechanism which really just helps enforce your intention that this class not be instantiated. It's by no means an essential feature, but it can be slightly helpful, especially when you're working with many programmers. So one programmer declares the class abstract, thereby preventing anyone else from mistakenly trying to instantiate it. So now that we've looked at classes, let's look once again at prototypical inheritance and see how that's different. If you recall in JavaScript, we create just what are called objects, but there's this way in JavaScript, rather convoluted way, whereby we can link the objects together such that when you do a property search on one object, it then follows up that link to the other objects until it finds the property of that name. What you end up with in this arrangement is effectively you can have an object which represents a class, and then anything that links to it can be the instances of that class. So the weird thing in prototypical inheritance is you don't have any formal notion of classes. You just have a bunch of objects and they're all linked together. And it's left up to the programmer to treat certain objects like classes, give them methods and fields, and then produce from those objects instances which link back to that pseudo-class object. I'll emphasize once again, this is really kind of a strange approach. JavaScript's really the only language of any note that does it. Every other major language with object-oriented features has a formal class mechanism. Lastly, once you get comfortable with the basic ideas of object-oriented programming, you'll probably want to read up on what are called design patterns. Design patterns in object-oriented programming are pretty much what they sound like. They are common ways of organizing classes to solve general recurring problems. The term design pattern was coined in the early 1980s with the release of this book, Design Patterns, Elements of Reusable Object-Oriented Software. The book became very influential, and the authors are now collectively often called the GOF, the Gang of Four. If you do read the book, you should understand that it's now quite old, so you'll want to supplement that with some more updated information on design patterns, because in some cases people's thinking has changed a bit. And you also very much should keep in mind, a lot of these design patterns actually aren't necessary at all in dynamic languages. Dynamic languages have a few features that make a lot of these design patterns really just unnecessary. However, even if you do work just in dynamic languages, it's probably good to be well versed in at least the most common design patterns they describe, because they have certain names, things like flywheel and observer and other such names. These names often serve as convenient shorthand for programmers when talking about certain common patterns.